Hi, this is the Imagine RT pitch for the MSD2 project for P14646, the Robotic Manta Ray. This is made by Kiefer, E, or Jonathan, Evan, Cody, Orlando, also known as Elizabeth, Diaz, Jaden, and Steve Erswim, our mascot. So, our team from left to right, as I mentioned, was Jonathan Goodman, who is an EE, then Elizabeth Orlando, who is a Mechie, Evan Strickland, who is another Mechie, Diaz Nino, Biomed, Jaden, Biomed, Cody, EE, and Kiefer, another Mechie. So our problem statement was to design a robotic manta ray that looks like a manta ray using soft robotics, moves like a manta ray, uses either remote control or pre-programmed path to look like a manta ray, and it can swim in water. So the motivation was based off of the previous states of projects. So currently, the Manta robots do exist, but they use rigid structures and actuators or bistable wing mechanisms. The desired state of the project was that the Manta Ray should be powered with soft robotics with the goal of a more efficient and biomimetic operation. So going into this project, our expectations were that there would be a simple muscle design that was modeled off of previous designs. We didn't think this would be easy per se, but not that it would be as time consuming as it ended up to be. We also expected that the waterproofing would be done earlier on within the process. We also expected that there'd be quicker integration of the electronics and quicker implementation for a functional skin for the manta ray. And we also expected that our movement system would be sensor based. So going through our process, this has been split into the mechanical section with the muscle, fins and body, the pump and waterproofing, and this ends up going into the electrical and software part that is mainly the programming. So for the muscle design, we started with the cast, which is at the top of the screen, and it produced the features that were expected. It created a successful inner chamber, but the material was not rigid enough and the chamber popped from the water pressure. Due to these designs and material choices, it resulted in using previous muscle designs, which is the muscle depicted on the bottom. For the fin and body design, the development was focused primarily on more easily tested modules, and this required geometric features that would be clearer once internal components had more iterations. And these easily tested modules would be things like dry boxes and muscles. So for actually modeling the fin and body, this meant that it was printed in multiple parts and it was molded in assembled pieces. So on the screen is one of the molds of the fin model. Now for the pump design. This is the CAD model for the pump, and the central hub was modified to increase strength and reduce the bill of material complexity. And the back face was modified to match the motor boss. So some of the tests that were used for this pump were a flow rate test, a leak rate test, and an occlusion test. And this pump would be implemented with the tubing. So specifically for the occlusion test, some of this would mean changing the occlusion so that the motor would spin correctly, so then the tubing could be fed through the pump. And there was possibly a low flow rate from the small scale and a risk of tube collapse from shorter roller separation. So as I mentioned earlier, the pump would be integrated with the pump tubing. So the turn mechanism has a code implemented to have an automated turn, and the pump occlusion would be altered for this better turn mechanism. So on the top left, you can see the tubing being fed through this pump and motor setup. And on the right, we have the Arduino board that's connected to the computer that has the code that would then power the turn mechanism for this setup. So for the internal body design, the peristaltic pumps would be stored in this custom dry box, which is in a 2x2 configuration. M3 screws were used to provide compression to seal the surfaces, and permanent cable glands were at the dry box interface, where there would be 4 outputs with 1 input, and this is made with solvent welded acrylic that is 1/8 inch thick. It is PDMS potted with the inlet outlet interfaces and cast with a PDMS EcoFlex gasket. Similarly, for waterproofing was the driver dry box. Here there's 4 stepper drivers, Arduino Uno, and a battery placed inside. So the wires would be run to the pump housing via 3D printed connection. This location is still being determined as it's dependent on the manta ray skin geometry. And similar to the last waterproofing box, this is made with solvent welded acrylic that is 1/8 inch thick. And once again, it is PDMS potted for the inlet outlet interfaces and cast with a PDMS EcoFlex gasket. So for some of the constructed setups, we currently have only 1 motor and its controller connected for the testing. Conclusive testing with the singular setup will lead to development of the other 3. We will work out the logistics and cable management and component housing prior to installation to accommodate for a smooth transition. And then as for the battery performance, we will measure our battery performance and ensure that itself and its related components meet expectations. And this setup involves the wiring and the motor. So as for movement, to prove a proof of concept, it would be by using a simplified automated movement. And our original plan was to have an autonomous movement system with sensory adjustments. The plan was to begin incorporating these sensor inputs and validate the movement system. But the problem was that the time it would take to implement all the sensor functions and integrating any new component advancements was just too much time for the scope that we had as we focus most of our time on the muscle. Now for the code implementation, the objective of the code is to validate that the components and the system work as intended. The code will update prior to full hardware implementation so that testing can commence as soon as the hardware is prepared. And the software will shift into an automatic motor movement program to operate the pumps and thereby the wings of the manta ray. So then it plays into the movement of the manta. So thank you to our sponsors, Calvary Robotics, and a special thanks to Dr. Lamkin Kennard, who guided our team through this project. Thank you.